applications, dynamic programming. There's a lot of broken stuff here. I have to move stuff around a little bit. So before I forget, I may not make the office hours today. I'll be there tomorrow. Today I have a promise. I have an appointment and I'm not sure if I'm going to make it. I think some PA. I don't know it. Okay? And another thing is we have a midterm on March 3rd, right? That midterm includes dynamic programming, but not anything after. So we're going to finish dynamic programming this week. And then we're going to do other things. And I don't have a note that I need, so I'm going to have to have it on my computer because I didn't have a way to print it. So where are we? We were at the screen abstract, right? So when are the homeworks due? There's 2 dynamic programming homeworks. When are they? This Thursday and next Thursday. Just in time for the midterm, right? All right. It's a good idea to do other dynamic programming exercises, if you can. So once you finish those 2 homeworks, you know, there's plenty of dynamic programming problems that you can try. So the screen knapsack, it says, so there's a bunch of items. They have values. And they have weights. And they have a knapsack capacity. Z. So the objective is maximize sum of values subject to sum of the weights in a subset, right? In a subset. Smaller than Z. And we were, I think we've been quite a few steps in this problem. We had the idea that in general, we're gonna need a Z in the recurrence, right? And we're gonna need some sort of item set, right? And that was something like max over all the values that you can pick. You know, that's pick item I, right? I get that value plus the best I can do in a knapsack of capacity, Z minus that item, and some notion which we don't know how to do yet. I have to take that item out of the set because I've already picked it. I can't pick it again. But then we said, order, fixed order arbitrary. So we pick an order of the items. And then I said, we can solve this problem if we use a fixed order. It doesn't have to be by values, weights, ratios, nothing. Just an arbitrary order of enumeration of the items. We said this could be solved by saying, I have Z, the item set, which we're going to call IN. So we say every item set IK is the one that includes all the items in this order up to K. So this is our original problem because we have all the items and the knapsack capacity Z. And then we say, we don't want to think exactly like this. We said, instead of saying maximum of all possibilities, we want to think of this subproblem structure as two possibilities, not all the possibilities. Normally, when you write the optimal solution structure, you're thinking, okay, what are my possibilities here? Which item can I pick first? If you remember, we had in the optimal solution, those are the weights, right, that are being picked. And we say, anywhere you chop this thing, this have to be optimal for this side, this have to be optimal for this side, subject to a constraint that once you pick some elements, you can't pick them again. And then we say, okay, if I can chop it everywhere and obtain two subproblems that have to be solved optimally, I'm going to choose to chop it at the first element. That's where I've got this recurrence. It says, which one could be my first element? Well, it could be any one of the items. But now I'm saying, I want to think of all possibilities, but not partition that way. This is a partition of all possibilities. It's saying you can choose the first item, V1, then do the best you can for the rest. Or you can choose item I2, do the best you can. Or you can choose item I3 and do the best you can. So you have n possibilities for choosing this thing, right? I is going to be between 1 and n, right? And do the best you can, and choose the one that's best. That's meaning choosing the first one that's best. I want to think differently. I still want to have a partition, but I don't want to partition by all the possibility of choosing the first item. I want a different partition. The number of possibilities is the same. It's the same n possibilities. So I'm going to choose a partition into two cases. Okay, which are the two cases? Either choose the first item or don't choose the first item. Now those are the same possibilities as before, because don't choose the first item means choose one of the others, right? It's not like I'm changing the items I have or the ability of filling the knapsack. I just think of the possibilities that I have in a slightly different way. Either choose the first item or don't choose the first item. Overall, that's a partition because I'm counting all possibilities. Obviously, any possibility is either with the first item or without. And I'm not counting anything twice because those cases are distinct cases, right? Are disjoint cases. Okay? So how would I write this? Now, assuming I have this fixed order, what are the possibilities in here? It's still a max, but it's only a max of two cases, right? So what is the, so it's max between, what are the options? Choose I1 or don't choose I1, right? Those are the two possibilities. So if let me write it differently. If I either choose I1, what would this recursion be? If I decide to choose that first item. I get that value of that item, right, because I choose it, plus the best I can do is Z minus WI1, and the item set, I have them in the wrong order. If the item sets are from the beginning to K, now I have to choose or not choose the last element. Because what I want is to have a different item set here, right? So if I say choose the first element, the item set will be this one remaining, and this one is not my definition of the item set. I could change the definition for this to be from K to N, right? So what should we do? Should we choose the definition of I, or should we choose the last item? Choose the last item? Sure. So this is a symmetric views of the problem. It doesn't change. I can either choose to define I from 2 to K, or if I stick with this definition, look at the last item, because when I choose the last item or don't choose the last item, my item set will become the next IK. Right? So let's say choose IN, and then I get VN plus these N item set, N minus 1, right? Which is who? This is I1, I2 up to I minus 1. Or don't choose IN, the last item. In each case, I don't get nothing for the value because that's not in, but I have the subproblem of, I have the whole knapsack and still item. So the main advantage in thinking this way as opposed to this way is not necessarily that's 2 versus n cases. Because this case actually is complicated. Don't choose item IN means you still have a lot of possibilities. The main advantage is the structure of the item set. By thinking this way, we solve the problem of, okay, this max doesn't bother us too much. N possibilities, we can check all n of them, pick the best one. What bothers us is this item set, right? If the best possibility happens to be I5, once I take the item I5, I have a subset that's now I1 to I4, and then I6 to IN. And then the next round I choose some item set. It's hard to represent those item sets because the number of possibilities of taking one item out becomes a lot. In fact, we looked at this and we say, if I want to represent my computation table, obviously one axis will be Z, right? And in here I have to have the item sets, right? If I allow arbitrary in and out in the item sets, there will be too many possibilities here. If those are n things, there will be 2 to the n possibilities. But if I can fix an order and have the item sets definitely go in that order, as in the first decision is made for IN. The second decision is I minus 1. Third decision, I force this order, then the item sets cannot be arbitrary subsets. They have to be prefix subsets. Again, this problem, I can write it the same by going from I1 and write the item sets K to N. To be the same exact thing. Instead of going this way, I go in that order this way. And another critical observation is that I can pick any order. This order has nothing to do with the weights or the values or what objects will be or items will be in the knapsack at the end. It says you can make a decision on these items one by one in any order you want, fixed order, but you can choose any order. The reason you can do this, obviously this cannot be greedy, right? If I show you this order of the items and I'm asking you make a decision right now about I1, you can't. You can't decide on the spot if I1 is a good object to put in knapsack or not. Even if it's not a big value or a small weight or whatever, it may be the right object to fit in the knapsack. But if you solve subproblems first, you can go in this fixed order. This is one of the dynamic programming that after you settle on dynamic programming the fourth parts, you need to spend some time thinking, okay, why this works. It's a little bit tricky wrinkle on it. So if we do the computation table, what we're going to have here, for a particular z and for a particular ik, this is c of z and ik, which is the best value you can get to the knapsack of size z, and the items, who is ik? I1, I2, up to ik, in that fixed order. Which I can pick a random order. So ik is not any set of k items. It's this particular set from ii to ik. Now this way, how many ticks I have on this axis? This is an n linear thing, right? So I don't have the problem of the number of possible subsets being exponential, which it is, right? It's 2 to the n number of subsets if I let it go free. So this is linear, and this is, of course, linear in Z. Right? So now, if I have this, not too hard to do the computation. Computation is piece of cake once I have this recursion, right? I mean, let's do it really quick, see what we get. I have to knapsack, discrete knapsack. Maybe fixed order, I1 I2 up to IN. That could be a random order. Could be the order in which I'm reading the elements, for example. I don't have to set an order, I just use the input order, right? And then maybe there is some init phase. I'm going to let you guys figure that out. How do I initialize this table? I have to set some things to 0 maybe and stuff like that. So how is this computation going to go? Where are the subproblems? If I want to solve this problem right here, what subproblems I need to have solved by looking at my table here, my computation? Where is z minus something? It's down. Z minus something is down, right? So this is z, and this is z minus some item. And where is I k minus 1? Is left, right? So I may have this. This is ik minus 1. So I have two subproblems essentially here. If I choose this element zik, right, it's going to be this subproblem because I lowered the knapsack and I have that set. But what if I don't choose that element? It's still same ik, but z remains the same, right? So let's write down who this is. This is z minus wik, z minus wik, and ik minus 1 set, right? And this one here is who? Z and ik minus 1. So I need those two subproblems to be solved when I have my knapsack. To solve this problem, you can put a star to it. That's the one we want to solve. I'm putting two arrows. I need those two to be solved. Some people in some countries study dynamic programming on this table because this mechanism, what subproblems needs to be solved before I get to my main problem. Of course, there's arrows everywhere here. There's some arrows pointing to this one from other problems. This is the dynamic part in dynamic programming. It says, in each order do you need to solve all those problems so that when you get to this problem, those ones are solved already. In principle, we solve all the problems. So don't bother too much with efficiency steps that are, maybe some problems in this table are not necessary. That's true. It may be that we can save some time by not solving some problems at all. There may be some problems we don't need. But in general, you want to solve all these problems. The trick here is what order do you solve them in, right? Because once I solve, so obviously from here I need those two. Can I solve it column by column? If I solve it column by column, it's going to work. If I have all columns solved when I start this column, can I do it? How about row by row? If I have this row, this row, this row, I can do it with the condition that on every row I solve problems left to right. Right? If I solve it column by column, I don't have to worry about it. When I get to this column, all the problems in this column will be solved because it's the previous column. If I choose to solve it row by row, the only constraint is on each row I have to go left to right so that this problem is solved before this problem. Again, some people, and I don't think that's the wrong thing, I think that may be the right thing. When they study dynamic programming, they actually, the first thing they do before anything, they draw this table. Say, where are my subproblems, and what problem depends on what other problem. This should form a DAG, which we don't, not ready to talk about DAGs right now. But if this dependency doesn't form a DAG, aka, then there'll be a problem. If there's cycles in this graph, there's no easy way to start. Because everywhere you start, you need to solve some problem that's not solved yet. So then, interesting question, what do you do? But that's for later. Normally, they solve a DAG, and you can see here why it's a DAG. Everybody points to the left. There are no cycles, because a cycle would mean something has to point back to the right. So because it's a DAG, we solve it in the DAG order. We can sort the DAG, right, easily. We didn't sort it yet, but 3 weeks from now we're going to sort DAGs. And then we can think of a DAG approach to do this. But in general, it's not necessary. I personally find it easier to think of a table if the dimensions of the table are not more than 2 or 3. If I have a lot of parameters, like 5, it makes it harder to think of this table. Thinking in a DAG may be easier. Okay, so how do I do it? What did we say? Column by column? So what's the main loop? For k equal, let's assume I already solved this. This is 0, like I have no items. Let's assume I have this solved already. This is 0, meaning the empty set, right? 0, k means no object, means the empty set.
When we don't choose ik, so we are choosing some other element, right? So
yeah.
How does that remain the same? That would
so when we don't choose ik, it's a bunch of possibilities. We don't say which one we choose. We only say don't choose ik. That's my way of saying partition the possibilities into either choose ik or don't choose ik. So if we don't choose ik, I'm not specifying which element we're going to choose. I'm only saying you have the same knapsack, because you didn't put anything in, and you can choose the best you can from the remaining k minus 1 elements.
After this.
Right, so then what would be the next question? Suppose I'm saying try not to choose ik. I'm here now. And here, what do I ask? What's the question now? Choose ik minus 1 or don't choose ik minus 1. The reason this works, it wouldn't work in a greedy, because in a greedy fashion I can make that decision right now. But the reason it works is because I already have this problem solved. Right? That's the dynamic part. If I have those problems solved, I know which one is better for me. Meaning either this or this plus vk. Does that answer the question? This is a fundamental issue here. Again, I know I've said it. Well, I spread knapsack on 3 lectures now. Yeah, that's on purpose. That's not an accident. I want to keep repeating knapsack until it drills down into your minds, okay? Why is it that I can say either choose ik, that's obvious, right? That's the same like choosing coin or choosing step or do that. The other option is not choosing a different coin, but says, don't do that. That's different than in coins. In coins, we said you can either choose coin D1 or D2 or D3. Right? In here, we say, no, we're going to do something else. Either choose that coin or that object, or don't do it. That's something you guys, once you learn all dynamic programming, I would spend some time thinking, okay, how did that work? Why does this cover all possibilities? Or here's an exercise that you can do. Can you try to fool this program? Can you find an example of objects and items where by doing these options, either choose that item or don't choose it, somehow, in the end, you don't get the optimal solution? The answer is no. But by trying to play with weights and items manually, here's my 5, 6 objects. Here's my weights, here's my items. Just to see how this program working on this. That could be a good exercise. Okay, so for k equal 1 to n, right? Those are the columns. And then for z equal, z has to be discrete. So that's a condition in the original problem, that z is discrete. So for example, the weights are integers, and z is also an integer. Doesn't have to be integers, just have to be a discrete scale, like maybe every quarter of pound or something like that. From z equal 1 to, I have some sort of max z here. C of z and k is who? It's the biggest one of those two, right? So it's a maximum of 2 things, either C of z minus w, ik, and k minus 1. So k minus 1, I can represent just the index here. I don't need an I. It's just the index of the which object I'm at. Or C of That's plus b I k, or c of z and k minus 1. And then I have to return something. So that's part 3, so to speak, computation, right? And part 4 was tracing the solution. See, we don't need to just output the maximum value. This outputting the C will say, I hope you guys remember, this is always the objective, so this is the maximum value. When we output a solution, we also need to output which objects were being picked. So how do we keep track of that? We need to add something here to track the solution. C is going to return the maximum value is 75. It won't return which objects to pick. We need to keep track of F, Z, and K. Usually those are the same parameters as in C. But CS doesn't indicate the value, indicates which subproblem did you go to. That's what C indicates. In this case, which subproblem means did you pick item K or you didn't pick item K. But that depends also on Z, right? If I change Z, I may pick item K and on different Z items, so it makes sense to have both Z and K. So what do we need to write here? It's only two possibilities. It's either 0, 1, right? It's either pick K or don't pick K. So we could say, depending on which way it goes, I'm going to add it here. That's illegal. You guys can do that. Only me. Only I can do that. Z of, what do we have here? Z of W, no, Z of K minus 1. So if this happens, I'm going to make S and Z and K equal 1. I pick item K. And if this happens, I'm going to make Z of Z and K 0. So that's going to keep track at that Z. It's not a constant for K. At different Z's, it may be either 1 or 0. It says at that Z and K, when you get to that problem, do you want to pick that item K or not? And then, obviously, I can trace this solution, right? How do I trace it? The Z is written here. So the trace, I have to start with Z and N, right? So for Z and N, I do what? What's my first thing to print out? I have to print something like for Z and N, print S of Z and N for item N. That's gonna tell me, did you pick item N or not? And then, how do I move down the solution? That's just gonna say, print either I picked that item or I didn't pick that item. Then where do I move? N equal N minus 1, because I'm going down, but then what about Z?
Z minus I.
Z will either be Z if I didn't pick the item, or so I could say Z minus S of Zn, that's 0, 1, times W, right? This is saying if this is 0, I keep the same Z, but if it's 1, I decrease the Z, right? So then, of course, I have to loop this. Loop until something. You guys have to figure out until that. So I start with Zn, I print the last item, I go down, meaning I go either on the same Z if I don't choose an item, or I go down if I choose it. And then I have to print, I think you guys can see because of this table here. Right? I go down until N equals 0 or something like that. It's not loop, it's a while for 4. Again, I can write these things. You cannot write loop and things like that on your exam papers. You have to write the proper pseudocode. I follow more intuition than I want you guys to follow my way of thinking more than the form of pseudocode. I trust that if you need a for loop or a while loop, you know how to write that in here, right? So you can't write loops like that. Okay. So one more thing about this problem. What's the running time? Running time would be, there's 2 for loops. There's some initialization, the first column is 0 or something like that, I don't know. Right? That's easy. The 2 for loops. So this is Zn. This is just gross approximation. 4 is Z times N. So here's the naive and incorrect runtime analysis. I'm only doing this for this problem because I want to put a splinter, plant a splinter in your mind. O of Zn is linear in both Z and N. So that means linear in both inputs. AKA, if N is fixed, this is linear in Z, and if Z is fixed, it's linear in N. So you can imagine I have a certain knapsack that's fixed 100 pounds, and the only variable is N, then it's linear in N. And I have a fixed number of items, such a museum, and I want still paintings, but I have different kind of knapsack I can go to steal my paintings, right? That's Z. Why is this not correct? I'm not talking at all about the fact that it's a product of 2 variables, and the product is not technically, mathematically linear form, it's a quadratic form. We say linear in each input, that means it's a linear in the product. One of this linearity is not quite linear. Which one is that? It's not linear in Z. So it's definitely linear in Z, but Z is not really the size of the input. So the big warning here is that Z is not linear in input size. Is N linear in the input size? Yes, because I have to get an array of N elements. Right? But what's the input size in a computer sense? How is Z given to me? What is Z?
Like a constant.
Z is a value. So how many bits are used for Z? When Z is passed to me, say Z is 1,000. How many, what's the input size? Input size, how many bits are given to me to write this value down? When a number is passed, how many bits is written for that Z? Hmm? We're talking general. It's not, yeah, but that's what if I want a really large Z? Log Z bits. So technically, Z is exponential in the size of the input. That's not the same for N. If N is 1,000, then the input size is O of N, right? Because these are N objects, they are passed to me as 2 arrays. If there's 1,000 elements, I'm going to have arrays of size 1,000. So when I talk about N elements, the input is really linear in N. When I talk about the Z, the input is not actually Z bits or Z bytes or anything with Z. It's a number, so it's log Z. So purely mathematically speaking, Z is exponential of input size. So this, in that sense, this solution is not polynomial because it takes z steps when the input size in z is actually log z bits. Of course, this doesn't bother us so much because in practice, for these problems, while theoretically speaking, this solution is exponential in the input size. If somebody asks mathematically, okay, how efficient is this solution? It's running time, it's always a function of the input size, right? We say in n, the number of objects is linear. In the input size for z, which is log z bits, because it's a value, it's exponential. So theoretically, it is what it is. Can't be done any faster than that. But it's not a practical concern. In practice, most z will be written on a fixed number of bytes, right? I mean, knapsacks will be written in integers on 4 bytes or 8 bytes, and that's it. Nobody will go with these z's to the point where I really need, like, if z really grows like the number of atoms in the universe, right? Then the number of bits becomes 20, 30, 50, 80, and z becomes 10 to the 80, right? Then yeah, this is a problem. Like if I have 10 to the 80 in here, the input size, it's only 80 bits. I mean, I'm talking base 10. In base 2 will be, I don't know, 300 bits. This would be too many sub-problems to solve. It would be 2 to 10 to the 80. I can't solve that many sub-problems with a normal computer. So theoretically, when you talk about z, if z is really allowed to grow to like really big numbers, this is an exponential solution input size. I can represent the input size log of z. Even if z is 10 to the 80, I only need, 200 bytes to write that number, no problem. But I can't solve 10 to the 80 sub-problems. There's too many. That is maybe a tricky question in an interview. Somebody tells you, you have this knapsack, you find the solution, right? It's linear in z. But be careful that the input size is not z, it's log of z, because z is just a value. In practice, of course, for most such problems, even in production environments, z will be something limited to 4 or 8 bytes, so you don't have to worry. A much bigger problem is the fact that z may not be discrete. It's not unbounded, so it's still like, 4 bytes maximum. But it's not, you cannot add ticks. See, the reason we can solve these sub-problems, so this is the other thing that's a big deal here. Z must be discrete. Meaning, z can be allowed to be anywhere on some fixed number of ticks. Integers, it's an obvious scale, right? Integer is 1, 2, 3, 4, up to something. I can pick half integers. 1, 1.5, 2, 2.5, 3, 3.5. I can pick quarters integer. 0.25, 0.5, 75, 1, 1.25, 1.5, 1.75, 2. As long as this is a tickable discrete axis, I can solve it. Why can't I solve this problem this way if z is an arbitrary real value? Because I can't go, when I say this, what for loop dice in here? For z equal 1 to max, well, just a real values, you can't just enumerate them. Right? So if z is, what happens if somebody says z is a real value, capacity, and you have those weights which are also real values? Right? What do you do? You can't do this for all z's, right? Z's, what are all z's? It's a discretization that doesn't work. What if I say z is a real value, but the items, the weights, are, say, integers? Can I solve the problem now? If z is a real value, it can be pi, or 3 pi or something, but the weights are integers. Can I solve it just for integers, even though z is an arbitrary value? If the weights are integers? Why yes or why no? So again, I'm changing the problem. Z is not an integer anymore. Could be 3.756A924, right? Some value. But the weights are integers. How do I solve? Why can't I say I can still solve the problem because I only solve it for integers. The reason is, any set of items I pick, the sum of weights will be integer. I don't have to worry about any z that's not an integer because if it's 3.56894, the maximum I can feed there is 3. So how can I do this if the weights, I need a property on the weights, right? Z is not a big deal because I can restrict z to only the z's that are valid. So how do I discretize z axis? I have to get from the set of weights, which is W1 to Wn, what are the possible values? Forget about z for a moment. Z is the maximum, but if I look at those weights, what are the possible total weight that goes into my knapsack? Sum of all possible subsets. So I need the possible, so this is the possible total sum of weights is the sum for any subset, right? When S is a subset of I1, I1, 2, 3, 4, up to N. So this cannot be done, I don't think, you can think about that, if somebody gives you a bunch of weights that are real numbers, say N weights, N equals 10 or 20 or 50, how many subsets are possible? 2 to the N subsets, right? So if I say, here's weights, 20 weights, how many possible sums, at least in theory, I have? 2 to the 20. Those will be my ticks. I need to compute my subproblems for those sum of weights, right? Because anything in between those sums, it's not possible. How can I solve this problem? Theoretically, this cannot be done in less than exponential time. So if I want to compute the ticks I need on the y-axis there, on the z-axis, I have to check all the subset sums for a bunch of weights. And even if the number n is relatively small, like 10 or 20, the number of subsets, possible partial sum of these weights could be 2 to the 20. So there are some, later on in the course, we're going to talk again about these problems. How do you check or how do you do something when you want to know all the partial sums of an array? So you have an array of real values and you want to know all the subset sums of it. It may be that the actual number of ticks is linear. I go through all 2 to the n subsets. In what case I get not 2 to the n values? In the case of some of the subsets, end up having same value. And that's quite possible. You know, if those values are, say, I don't know, number of courses taken or things like that, ages, when you add them up, they could get, a lot of the subsets have the same value. But to get the actual values that are possible so you can construct this tick axis here, that's a tricky question. So I think if you get a dynamic programming question at the interview, even though this is a simple solution, there's a problem on the z-axis. What are the ticks in here? Even though they are a linear number of ticks, if those are ages from 0 to the maximum sum of them, that's a bilinear axis. But which ages do I need? That's not an easy problem. We're going to talk towards the end of the term about how to do those. When we talk about approximation algorithms, we specifically talk about if the problem is exponential, what do you do? You can find a solution, but you can find an approximative solution, and you pray it works, you know? I just want to let you know that discretizing the z-axis here could be a tricky problem. Not a problem if z is integer and the weights are integers, because then I just put the integer axis and I'm done. I don't have to sum the partial weights if everything is integer. I don't need this step. I say, just compute all of them. Even though some z's that I have here are impossible. There is no way to pick a set of items that sum to this z, right? That can happen. I have from 0 to max, and it so happened that no subset of items will sum to this tick here. So I don't need that line at all. That's okay. I'll compute it anyway. Right? Because I only have so many problems, and I'm fine doing all of them. Good. Now we're done with this one. Let's do another. Use this board first. So the next problem we have about 3 problems left that I'm gonna do on the board. And then we'll talk at office hours about some of the problems in your homeworks. So the other problem that I want to talk about now is called LCS. So that is, what is LCS stands for? That's a note I don't have, so I'm going to have to cheat by looking at my computer here. Longest, L stands for longest. Common. Okay. So what this means is, I have I have 2 sequences. X1, X2, up to Xn. So that's a sequence. The order matters. And Y is Y1, Y2 to Yn. This is the input. The objects here don't matter what they are. They could be numbers, people, emails, documents, images, whatever. There's some items and some other items. We're not going to use any numerical fact on those items. We only care about if one is the same as the other. So the only thing that's available here is this item same as this item, is this item same as this item. So for 2 items, we know if they are the same or not, but we don't know what they are. I'm gonna go even further and saying this is the input, but in general, I'm gonna call xk the prefix of k items in X. So who's gonna be xk? The sequence, x1, x2, up to xk. And who's gonna be yk? y1, y2, yk. That's for any k. So when I say, so in that sense, who is this? This is x, m, and who is this? Y. So what's the task here? What do I need? I have to find the longest z1, z2, up to zl, right? This is a sequence. So what's the thing about sequences? Why is sequences different than sets? Order matters. That is, this is part of X's, right? So this is a subsequence of X, and also a subsequence and Y. I think you have a problem in the homework. I showed you at the greedy chapter that's actually solvable this way very easily. Okay, so this is, once we see the knapsack and we understand the knapsack, especially that trick with picking the item K or not picking the item K, this is easy. Related to that trick, when you go home and you study the knapsack problem, in many midterms I have a variation of the knapsack as part of the midterm, okay? fail warning. Some variation, like there's some knapsack plus some constraint, or knapsack reformulated as a different problem. There's a barn with horses and cows, and it's a knapsack, but it's just not written as knapsack, okay? And if you realize it's knapsack, it's easy, but it's the same problem, right? So what you want to do if you get stuck at how can I pick item K or don't pick item K, remember, go back to we did a problem before knapsack, n choose K. We thought exactly in the same way. When you do n choose K, you fix an order of the items. You don't care what the items are. You fix any order, and you say, if I want to choose K items, either choose the last item or don't choose the last item. Those are the possibilities. And if you choose the last item, you have to choose K minus 1 from the remaining n minus 1. And if you don't choose the last item, you have to choose all K from the remaining n minus 1. That Pascal formula in combinatorics, it's the same principle as the knapsack problem. And same, in here it's easy, we don't have to impose an order. The order is given to us, right? So in here, we still gonna go do the same exact mechanism, but the order, we have to use this order. We can't say, arrange the elements in a different order at random. So, we start with part 1, right? Optimal solution, substructure, subproblem structure. Remember, I have to do divide and conquer. I have to make sure first that divide and conquer is going to give me the answer. So what is an optimal solution? If somebody gives it to me, how does it look? Bunch of z's, right? So here's it, Z1, Z2, ZL. That's the optimal solution. Now, of course, I don't have it, but if I would have it, what would I discover in it? So if this is an optimal solution from original problem, what's up with this ZL here? It doesn't have to be the last one. But last common is a ill-defined notion. Last common, like maybe this one here is common with this one here, but also with this one here, and this one is common with this one. What's the if this is the same as this, and this mark with the star is the same as this, right? Let me do this drawing again. Here's X, right? And here's Y, right? Suppose this one is the same as this, and this one is the same as that. Which one is the last common? I'm just saying, last common is a little bit of ill-defined notion here. I know what you mean. I'm sure you mean well, but last common is not clear which one is last common. So, yeah, that's the idea, last common. But we don't have to worry if we have the optimal solution, right? I mean, that's a worry we have when we have to solve the problem. Which one is last common? But when somebody gives me the optimal solution, I look at this ZL, I say, where is this ZL? ZL must be somewhere, because it's a common element, right? So I look at my X, right? And I say, where is the last ZL? ZL may appear several times in my X, right? But there is a point here, which is ZL. That's the last ZL. So this is last ZL in X. And there is a point where is the last ZL in Y. Is that guarantee that if this ZL in here, there's a Z, last ZL in there and last ZL in there?
Yes.
Yes. So it's not an assumption. If the solution contains ZL, then they have to be the last ZLs in there. What it means, I say, is that this other, the after ZL in X and after ZL in Y, they can't be any common element. So the number one statement I want to make here, part one, I don't know if this is A like before, but one thing. After last ZL in X and after last ZL in Y, no common elements. It's like a theorem, if you like, a claim. I can go ahead and prove it, right? Why can't there be anything common between this and this? That'll be part of the solution, right, after ZL. If this is optimal, we'll have all common elements, so that's not possible. So that tells me that I don't have to worry about this hashed out parts. If ZL is the last element, ZL is part of the optimal solution, is the last occurrence here and here. I can remove those parts of the sequences. I draw them as array, but they're really sequences, right? So then, now I'm cutting this X here before ZL, and I'm cutting the Y here. And the last statement I want to make is that the optimal solution without ZL, so let's say optimal solution only restricted to Z1, Z2, up to Z, who's this? ZL minus 1, has to be, this part has to be the optimal solution for what?
For X before Z.
For X going all the way from 1 to,
Minus 1.
let's say this position here is, it's something. Okay, let's say U, and this position here is V. So this gotta be from 1 to U minus 1, and Y has to be from 1 into V minus 1. In other words, if I look at the subsequence before ZL and the subsequence before the last ZL, the optimal solution common sequence between those two, so that is LCS of that, has to be the solution from the optimal solution cutting ZL out. Why is that? If this is not an optimal solution, there's a better one. Better means here what? What's the objective? The length. Is it unique?
No.
Is not unique. So I could have two subsequences of the same length. Fine. So it could be a different solution, but it can be better, meaning it can be longer. If it be a longer one, common between those two, more than L minus 1. If I add the ZL, I can add to anything, right? Anything common, any sequence in here, like this guy is the same as this, and this guy is the same as that, and then this guy is the same as this, and this guy is the same as that, and then this one, that's kind of a common subsequence, right, between those two. Anything that's the best, I add ZL to it, I get my solution, right? So that's part number 3. Optimal solution between X from 1 to U minus 1 and Y from 1 to V minus 1. If I solve this problem and I add to it the element ZL, I'm going to get an optimal solution for X and Y. Of course, I don't know who's U minus 1, I don't know who's V minus 1, and I don't know who ZL is. The point is, there is a U and a V and a ZL, such that if you solve this subproblem, and you put ZL back to it as a common element, you solve the whole problem. But we don't know where to break it. Like in all dynamic programming, we know there is a magic breaking point. We know we need to find this ZL, and we need to break it, and once we break it, we can solve the subproblems, right? Then put that element common back to it, and get the solution. But if we be greedy, we could break it right away. In here, we need to play with it to break it. The point of the part 1 is to say that there are those magic breakable U, V, and Z, and so on and so forth. And if you find them, You just go ahead and solve the subproblems, and you glue it back together. Gluing here is just adding the ZL to the whatever solution you get from the x. This will be x v minus 1. This is sorry, y v minus 1, x u minus 1. If I solve those LCS between them, I get the best sequence. I add one element to it. Good. Okay, so part 2. Who is C of x, m, and y, n? I use prefixes. Obviously, this m and n that will go down will be part of my recurrence, right? Part of my table there. So I have to look for this common element, like the one you said, last common element, right? Right. But I'm not going to try to find a common element. Instead of trying to find a common element, I'm going to apply a little bit of the knapsack idea. I'm only going to look at the last one. I'm not going to say, my exact question that I'm trying to answer is not which one is the ZL. Instead, I'm going to answer, is this the last ZL or not? If it is, bingo, I found it. The last two. If it's not, move on. It doesn't mean I found the ZL. I'm only deciding, like in knapsack, is the last element IK one that I need or not? If it is, good, I found it. If it's not, move on. And I didn't find it yet. I still didn't find the ZL. I'm just cutting the sequences out. You guys laughing at me? So, you know, laughing is very good. Let me say that. No, honestly. But do we understand? You're laughing because we understand this? Okay. That's hands up who's with me here. Okay, good. So I have to ask myself a question, which is x, the last one, xm, same as y n, right? Is it? So I may have a bunch of options here, right? So if it is, if yes, I found my ZL, right? If those two things are the same, I got the ZL. So well, then what? Will be that ZL goes into, this is the length, right? Max length of the LCS. So the fact that I found one common, what does it do to the length? Plus 1. So plus 1, that's the element I just found common. Plus, do the best you can between right? Because now this one cannot be used once I use it. Okay, well, how about no? This is not common. Right? So I can't just say, can I say remove it? No, because maybe it's common with something here. Right? I can't just say move on. You can, the fact that they're not the same, that occurrence, it's not matching, it's not part of LCS, but this element here might be common with something before, still part of the LCS, and this one might be part of the LCS in here. So I can't just say remove that, because I'm cutting part of the LCS. So what do? I have two options, right? Either cut it from X, and or cut it from Y, right? And do I have any plus here? No, because I need to find a common element. That's it. LCS, nice and easy.
What if the element is common but is not part of the longest sequence?
That's not possible, right? We just proved that in here. That if you find a ZL, the solution you find, I mean, I didn't prove it. I say I can prove it, but I didn't actually prove it. But it's a proof here that says if this is common, any optimal solution before it, plus that element, will give the optimal solution. And he's right. We need this before we start dynamic programming. if it says, what if it's common and it's not part of solution? If that's a possibility, what we're doing here not gonna lead to a correct solution, right? Because we under these assumptions that if we find a common element and we add it to the best solution, best LCS before that element, then that's an optimal solution for the whole problem. That's our divide and conquer principle here. To find the last element, if you find it, solve the remaining subproblem and just add that element back to it. So if we have to try to make this proof here. I think that's what he's suggesting. I don't have time for it, but you can try it. I think it's easy to see even how to prove that if I found a common element, there is no reason not to include it. Here's what situation might be interesting. This is common, right? But this is common to here, and to here, and to here, right? So this one matches like 4 times here. And this one matches some dot in here. I think somebody might ask, why pair this with that if I can pair with something earlier? Well, if I pair something earlier, now I miss this connection here, right? Because if I pair this with this, a subsequence has to be in order, so I miss this pair. But even without this, suppose there is no such thing here. Is there an advantage if I have multiple pairing to not pair with the last one, to pair with the one before? Right? If I pair here, at best I get the same solution as before. I can't get a longer sequence if I choose to pair earlier than I can, right? Whatever sequence, suppose I pair this way, whatever sequence before that was common, if this is valid, this will be valid too. So I'm not losing anything by picking the last one. That's what makes it solvable, divide and conquer. Now back to greedy. Can we choose greedily what to do here? Can we choose which of the subproblems we need without solving them? Because that would be greedy. So I think this one is obvious. If we find a common element, we can, this is a greedy sort of thing. Feels like greedy, right? If you find a common element, definitely put it in. You can think of this as greedy. Because we know right now that this is part of the solution. So that feels like greedy. The problem is in here. If I don't find a common element, I wouldn't know where to cut it from. And I can't cut it from both, because I may have some of them being a part of LCS earlier. So I need to solve those subproblems to know what's going on. That's why the problem you had with the longest common, what was it? Increasing sequence. It has to solve subproblems first. Right. Okay, so what's my computation table? What am I going to have in it? I'm going to have an M, right, and an N. And I look at this problem here. Let's say M and N. This is my problem for XM. I want LCS between LM and XM, right? So I have 3 possibilities. If the item is common, the last element of the sequence is a common element, then where is this going? This is M minus 1, N minus 1. So I may need this subproblem, right? What if it's not common? Where is M minus 1 and N? It's here, right? So this is M minus 1, N minus 1. This is M minus 1 and N. And this is M and N minus 1. So these are my subproblems that I need to solve to get to this problem. In other words, when we do bottom-up computation, remember when we do bottom-up, we solve each problem once in the right order, so that when we get to this problem, those 3 must be already solved. That's what we want to do here. And we now worry, what if this problem, it doesn't have to be solved? Somehow we don't need it. Which could happen. Not in this problem, but it could happen. We don't worry about that. We just solve all the problems in the table. But in the right order, so we solve each problem only once. I mean, it's not a big table, right? The order of computation here is going to be? Amen. Okay, so what's the order that I need? How can I solve these problems so that when I get here, this and this and this are solved? Can I go row by row? I think I can, with the condition that each row goes from left to right. If I solve this row, then this row, then this row, then this row, it's all solved. I could solve this assuming I go from left to right so that these problems are already solved from the previous row, and this is solved because I'm going left to right. Same idea with the DAG. This is a DAG that all points down. So how do I do that? Let's try to fit it in here. So this is bottom up, part 3. Again, there's some unique phase that you're gonna have to figure it out. Like, how do I start? What's on the first row here? So this is one element, right? Maybe. And what's in here? So what is 1 and 1? This is 1, this is 1. What is its value? So in here in this table, C is the length, right? So this value, if X and Y are of length 1, has to be either 1 if is the same, or 0. And what is this? This is 2. What is in this cell here? What's the maximum of length that can happen? So I have in here, x is this point here corresponds to an x of 2 elements, right? And a y of 1 element. So what is the possibilities for the LCS? To be 0. When it's 1. When it is y, it's one of those two, right? So you have to figure out how to initialize this thing, this procedure. But then I'm going to have 2 for loops, right? I say row by row. So for I equal, I'm going by the rows, so say I go by n. 2 to n, assuming I did the initialization for the first row. For j, I have to go in this order on each row, right? 2 to m. So that's essential. Each row left to right. You can put a comment like this sometimes, like in the code. So what do I do? Who's my C of I and J, right? Is it I and J? The first one was, the way we wrote it here is the M. So it's J and I, because the way we define C is with the indexes on the column first. We say it's, so let's put some if conditions to make it more clear. If x, j, that's the x's, is equal with yi, then c of ji is 1 plus else say we get a value, no, else if C of now, so I mean one of those two branches, right? If C of j minus 1I is bigger than I minus 1, then C of ji is the bigger one, right? C of j minus 1I. Else, C of ji is C of and then I have to return something. Now, how about the tracing? So I've computed all the C's. C's are what? The lengths. So at the end of this, I'll know the maximum length obtainable from XM and YM is 12. The maximum subsequence is of size 12. But I need to know now the actual subsequence. So I need to remember for each problem which one of these arrows I took, right? Which one of the subproblems gave me the path, right? What happens here, there's building a path all the way down. So I need to know how to follow this path. So in this case, S of ji is what? How do I keep track of this thing? I can write the pair where I went, right? J minus 1, I minus 1. That says go down. But that, I say there's only 3 possibilities here, right? This way, that way, and that way. So I don't want to store these random numbers here, j minus 1 and I want to store one of the possibilities. I'm going to store the arrow. Because which arrow do you go to? So I'm going to put a character that says go down on a diagonal, right? Because it's saying this is where it goes. Okay. People calling a lot. Okay. So I'm storing which way in my table the subproblem. What subproblem do I need to follow? How about in here? S, J, I, in this case, is who? Where did I go? Is this left or down? J is for X. So I go down left, right? And this way? But I don't think, because it's those 3 options, maybe I had a way to do it without. Maybe I don't need S at all. Is it possible to trace this solution without S? To actually print it out. Let's imagine that we want to print out this solution. But we're not going to use this S. So we start with M and N. And at Mn, how do we... normally I would say print. I look at S, right? So I say if S, I, J, Mn. Is it M first? No, it's N first, right? M first. If S, Mn is the down arrow, I say print. I have a common element, right? So which is the element? Xm, which has to be the same as Yn. X, the element. Because I found the common element. And then, where do I move? M becomes M minus 1, N becomes M minus 1, right? So that's one option. This is a loop on Mn, some condition. Figure out when it stops. What happens if Smn is the down arrow? I print anything? I have no common element, so I print this because it's common. And in here, I decrement who? I decrement n. And if this is if I could say else here, right? S of mn feeds the back arrow. I have to decrement. Then keep looping until I stop. Can I do this without S? Yeah, but how do I do this without having S? Oh, I only have C, right?
Just print it where it is
Print
common.
xj minus 1.
Well, I can print it right here, right, as you're saying, fine, but I still want to do my trace here, right? Separate procedure. How can I do the trace if I don't have this S? I only have C. How can I replace this condition with what? How would I know from C if this is the case? This is the same as saying C of Mn has to be 1 plus C of M minus 1, right? I could check this condition instead. If this is true, then it's that case on the diagonal for sure. Okay, so I can replace this with that condition. How about this condition here? What's the equivalent condition in C? C of Mn is equal with so instead of putting the condition in S, I can put it in C, and then you guys can figure out what this means. So I don't need this S. I could ask the same exact three conditions on C alone. You're obviously not going to lose points whatever you do. You know, like if be me and I'd be under an exam with, you know, I would just follow the recipe. I would have an S in there. But if you do it this way, it's obviously correct. It's fine. Sometimes it's not extra computation to do it from C. Normally, if C is a mean of several things, then you'd have to compute that mean again to figure out which subproblem was it. But in here, it's a 3-option thing. You can put it in C instead of. Okay? The running time is Mn. We'll have the notes available online. I think they're already there. So I think we're going to start the last problem I want to do today, and we're going to finish it on Friday. So there's 2 more problems we want to do. The one that we want to start now is matrix multiplication. We're not going to finish it. But this is a tricky problem. It's a different difficulty than we've seen before. So we had these difficulties with the knapsack. We pick item K, don't pick item K. And now I'm going to show you a different difficulty. The problem in matrix multiplication difficulty is going to be in the computation table. Like the order of computation is not going to be obvious. So far, when you see those tables, was clear in each way I need to solve the problems. For matrices, not that clear. So let me go here to this matrix multiplication problem. So the task is, I have matrices, A1, A2, AN, those are matrices. They can be multiplied. You know there's a condition to multiply matrices, right? Yeah. The number of column on some matrix has to be the same as number of row on the next matrix, right? So, for example, A1, A2, A3, A4, A5, and A6 The numbers I have here is 30 by 35. So first is rows by columns. This has to be 35 times something, otherwise it doesn't work. 35 times 15. This have to be 15 times something, times 5. This is 5 times 10. This is 10 times 20. And this is 20 times 25. So the other basic notion we need, when we multiply a matrix A times B, this is of size, say, P times Q, and this is Q times R. The number of multiplications, so this is order of everybody remembers how matrix multiplication works? There's a 4I equal 1 to B, 4 J equal 1 to R, 4 K equal 1 to Q, do something. Do we remember matrix multiplication? So the way it works, this is matrix A, this is matrix B, and the result is matrix, the product. Each object in here, it's going to be a row if it's in the, this is in the row I, J. This has to be the row I multiplied with column J. Okay? So every cell ij is the row I times column J. So that's how many rows times how many columns. But every row times a column vectorial product has to go through all elements in here, multiply them with all elements in here. That's the Q in the middle. The number of columns here is Q. The number of rows here is Q. So that's why for every cell I need to do Q computations. And this would be P times R. So it's P times R cells, but each cell requires Q computations here. That's why when I multiply matrices, it's PQR. Now I want to multiply all of them. So naively, you can do it from the top, right? You can say, you know, this times that, times that, times that, times that. My point may not be obvious. It matters in each order I do them. Another thing that I think everybody knows is that when I multiply 3 matrices, I can do it in 2 orders. As long as I multiply B with C and then with A, or A with B and then with C, I get the same result. This is not an obvious statement. You probably have done it when you studied basic linear algebra in high school, but try to prove this for me, exercise. That if you multiply the matrices B, C, and then with A, or A, B, and then with C, the actual cells in the result, in the final result, are the same cells. Cell ij here is the same as the cell ij here. If you never did that proof, you should do it once. It's only like 4 lines, right? But it's not an obvious as with numbers. With numbers, it's an obvious thing. In here, it's not. Because each product is a sum of products, each itself. But I'm counting that you've seen associativity of matrix multiplications before. So what happens here, because of this, I can do it, I can multiply, for example, A2 with A3 first, then with A1, then A5 with A6, then with A4, and then the result together, right? Associativity will tell me you can do it in many, many ways in here. So I want to prove before I even start the problem 2 things. Number 1, order of multiplication matter. That I just have to show you that with an example. Suppose I want to do A1, A2 times A3 in here. How many this is 2 multiplications, right? First A1 with A2 times A3. So how many multiplications would that be? A1 times A2 is what? 30 times 35 times 15. And then that's 1. the other one, it's a plus, right? Because that's how many computations I've done first. Then the other one, when I multiply this result is going to be what size? 30 times 15. So when I multiply the second matrix, the third matrix to it, I get what? Okay. So how much is this? Can anybody do something?
0 plus 150.
Do we have a? The whole thing is 2 to 5?
2250.
2250. Did you do it? Oh, is that right?
That is just the
So this is about 1,000 times 15. That's 15,000 by itself, right? It can do that. Can anybody do this?
18,000.
How much?
18,000.
Straight, 18,000.
Yeah.
Like that? Can anybody check? So I have two numbers. I don't want to put the wrong number, then it's on YouTube and everybody says, this guy can't even do multiplication. Let alone algorithms, right? We don't want to put it online.
18.
All right. But I could do this in a different way, right? I could do A1 times A2 times A3. So then what? This is A2 times A3 first, it's what? 35 times 15 times 5 plus, now the result in here is 35 times 5. So the second one is 30 times 35 times 5. How much is this?
Divided by
37875.
7875. I have that number. I have it in here, the notes. So, moral of this whole exercise, the order in which we do the multiplications will matter as part of operations that the computer does. Because this way, which be the naive way or the default way, right? Just multiply the first to the second, multiply the result to the third, will result in 18,000 operations. Meaning little multiplications. Sometimes in matrix multiplication, we don't count the additions. Remember we did something in the first class which says you just count multiplications. The multiplications are the heavier operation. It certainly used to be the case 10 years ago. Multiplications were much harder than additions for processors. Now things have improved because Intel and AMD and others were very hard. Multiplication is not that hard anymore, but still harder than an addition. Because addition is two registers on top of each other very, very fast. Multiplication is not, it can't be done that way, right? So if I know in which order to do it, I do fewer operations. So for, if you have 3 matrices, how many ways do you have to multiply them? So for n equal 3, there are 2 ways to multiply. Right? How about n equal 4? What I can do? I can do A1, A2 times A3 times A4. I can do what? A1, A2, A3, A4, like this way, maybe. I can do A1 times A2 times A3, like that, then A4, right? Is there more? Who go first? A1 times A2, like bracket here, before A2, A2, A3, like that, and then this multiply with A4. This I think is valid here, right? This is not one of the ones I have. Do I have it? This is not the same as this, because this multiplies A2 and A3 first, just like this one. But then this one multiplies with A1, this one multiplies with A4. So if there's any other way, exact order is A1, A2 here, times A3, times A4. This is A1, A2, A3, A4. This can be done in parallel. It doesn't matter which one goes for the jungle segment because they have nothing to do with each other, but then between them. And is there any way that I don't have yet? A3, A4 first, multiply with okay, and that's the only one I'm missing here. Now notice that every one of these things, while it changes the order, so different orders, but how many matrices get multiplied? How many multiplications of matrices I have? How many matrix multiplications are there? Three, right? So it's always n minus 1 matrix multiplication. That's obvious because every time you multiply, you're going to have to do n minus 1 multiplications. The question is in what order to do those. Now, here's a naive idea. I'll just check all of them, right? I'll say for 2 there's 2 ways. For 4 there's 5 ways. I can do the calculation without doing the actual multiplication, right? I can just do these calculations we done for 2 because I have the dimensions. So I can do how many multiplications are required here, how many are required here, how many are required here, right? And I'll do all these calculations and I'll know which one is the smallest number and I do it in that order. What's wrong with that? So again, I'm not doing the actual matrix multiplication until I know which way it is. I'm only computing all those ways, and I'm calculating here, here'll be what? 30, we already did this, right? A1 times A2 is A3 is 18,000, and then I'll add another. The result of A1, A2, A3 will be how big? 30 times 5. So times this one, I'll have to add 30 times 5 times 10. Right? So it'll be 18,000 plus that. So I can compute these values and then choose the minimum out of them. If I know, for example, this is the minimum, I'll do the matrix multiplication in that order. Yeah, everybody's following. What's the problem here? The number of ways is too big. So the number of ways to multiply and matrices or items in general, because this number of ways doesn't depend on those matrices or numbers or anything else, is approximatively order of 4 to the n. 4 to the n divide by something, perhaps? Let me give you an exact number here. N divide by 3, 2. It's take out at least that many. So clear an exponential value. Right? This, I'm putting a big star here. This is a very important number in mathematics. In how many ways, different ways you can multiply things. So for the ones of you who want to do something very interesting, this is called the Catalan number. Cn. In combinatorics, this is a very important notion. It has applications to geometry, physics, biology, the number of binary trees, the number of things that multiply, the number of populations multiply. There's hundreds of combinatorial problems that relate to Catalan number. Number of paths, maps, and there's books written about Catalan numbers. It's not part of our course, but if you're mathematically oriented, you should take a look at what Catalan numbers are. In my undergraduate math course, there are some lectures about Catalan numbers. The most important thing that we need for Catalan number is this recursion, which you guys have to prove. N minus k. It's very easy to prove. It's a 3 lines proof, right? So we're not gonna use this. This is a magic result. We pretend we don't have it. We pretend we don't know it. But this recursion, it's easy to prove that, saying if you want to multiply n matrices, here's how many ways you have to do that. It's a sum of all this. This is like recurrences, right? And then based on this, you can show that it's about that big, right? Once we have the recurrence, we can prove it's that big. The moral of all this exercise is that if you really want to enumerate all the ways in which things can multiply and calculate for each of them the number of multiplications needed, that's going to be an exponential problem. That's why we're applying dynamic programming here. We don't want to enumerate all these ways. So you guys have to prove this by Friday. It's in the notes anyway. It's very easy to prove because you prove it by induction. By induction over n. If n has this formula, C n plus 1 will have what formula? Sum from k equal to 1 to n of ck, C n plus 1. So you prove this induction, it's a very simple thing. And then from here to here, we're not going to prove this is hard. But we can easily prove it's at least exponential. Because proving that this is bigger than, say, 2 to the n, which is a smaller number than this, is very easy. And then we'll go back to dynamic programming. Now that we know the problem is too hard to solve by brute force, try all possibilities. How do we think of an optimal solution? Structure, bottom-up computation, tracing, so on and so forth. There is a trick in this problem, which is even if we do all that, the order in which we solve the subproblems to get a computation table done, aka to have the subproblems we need for the next problem, that's not obvious at all. It's not like by rows, it's not like by columns, it's something else that needs to be done. It can be done, but it's not obvious. Okay, so I'll be tomorrow at office hours. I'm not sure about today. I can't promise because I have an appointment. I'm sure I'll make it back. If is there any urgent thing, you can write me an email and I'll try to answer it. If not, we'll talk about it. Can we stop the camera? The red button on the right side.